So let's talk about elimination reactions. Philosophically, these are going to be the reverse of addition reactions. So I'd actually like to start by looking at a reaction that we spent some time doing. And that's the addition of HBr to an unsymmetric alkene. So in the forward direction, this is an addition reaction. And so there are many mechanistic steps that are involved here. You first have a proton transfer. Of course, that's going to form a carbocation intermediate. Then you'll have a rearrangement. And I'm going to push these arrows in a moment. And finally, you have a nucleophilic attack. So 3 of the 4 patterns of polar mechanism are involved in this simple electrophilic addition reaction. Let's look at all of the details now. So again, as in all addition reactions, the nucleophile is always the pi electrons. HBr is polarized because bromine is more electronegative than hydrogen. And of course, bromine has 3 lone pairs. So in the proton transfer step, we make a new carbon-hydrogen bond. Since hydrogen's a monovalent atom, it will yield its former bonding electrons that it shared with bromine to the bromine atom to form bromide. Again, we have a carbocation intermediate. The most stable carbocation that can be formed is when carbon 1 gets to hydrogen and carbon 2 has the positive charge. Also, we have a hydrogen bonded to carbon number 3, and that becomes important for establishing a rearrangement in step 2 of this mechanism. So the intermediate after step 2 is also a carbocation, but it's a tertiary carbocation, which is more stable than the secondary carbocation. Also, bromide is in solution, which was the leaving group when the proton transfer occurred in step 1 of this mechanism. And simple nucleophilic attack. This nucleophilic attack can occur from above the plane of this molecule or from below the plane of this molecule, so you get a racemic mixture of each of these. Of course, there is no relevant stereochemistry because we don't have a chiral center. So I can draw the major product as 2-bromo, 2-methylbutane. That's the addition reaction. The elimination reaction would be to begin with 2-bromo, 2-methylbutane, and we would employ the use of a reasonably strong base and also high temperatures. And what we would obtain would be an elimination product. Notice the elimination product we get is not the original alkene, and that's because the more thermodynamically stable product is going to be preferentially formed in this reaction. This is called Zaitchev's rule. And Zaitchev's rule is governed by the same stability criteria that Markovnikov's rule is governed by, and that's hyperconjugation. So the more internal double bond, the more alkyl groups that are attached to the carbons in the carbon-carbon double bond. Notice in this case we're talking about 1, 2, 3 of the 4, which would certainly be more stable than if we considered this molecule, for instance, which only has 1 alkyl group bonded. So we'll get an alkene as our product. We need a strong base. Let's talk a little bit more specifically about what strong base is. Hydroxide would work. Alkoxide would work. Amide would work. Or even a carbanion would work. So these would be examples of strong bases, but more importantly than that, the base also needs to be bulky. So while methoxide is suitably strong, it has a limitation in that it's not very bulky, which means it can act as a nucleophile. And if it can act as a nucleophile, then you're going to have substitution product that's formed and you'll have elimination product that's formed. If we want to favor elimination solely, we want a bulky, strong base. There's lots of examples of bulky, strong bases we can use, but one of the classic ones is T-butoxide. Usually the counter ion is potassium. On an ACS exam, you might see it written as KOTBU. This is one example of a bulky base. Another example of a bulky base is known as LDA. That stands for lithium diisopropyl amide. The idea with these bulky bases is they're too big to perform nucleophilic attack. They're also known as non-nucleophilic bases. Lithium diisopropyl amide. Its structure has a nitrogen atom only making 2 bonds, so it's negatively charged. It does make 2 bonds to isopropyl groups. This is a classic base to form enolates, which are reactions we talk about in second semester organic. There are also some even larger ones known as DBU. There's also HMPA. These typically are not on standardized exams. So LDA and T-butoxide are the 2 really big ones. In an elimination reaction, let's talk mechanistic patterns. You will see a proton transfer, you will see loss of a leaving group. Remember, in a substitution, you see loss of a leaving group and nucleophilic attack. So the proton transfer step essentially replaces the nucleophilic attack step. There are two mechanisms for elimination. One in which everything happens nearly at once. Not surprisingly, this is called E2. And one in which we form a carbocation intermediate, and then we have the relevant proton transfer. Not surprisingly, this is called E1. Of the two, E2 is by far and away the most common mechanism. So let's take a look at what an E2 reaction looks like and also discuss the stereochemical limitations of it. All right, so let's consider our previous example. This was the major product after our addition reaction. And so what I'm going to do now is give this a little bit of stereochemistry. So I'm going to put this methyl group coming out of the plane, put the bromine going into the plane, and of course I would have a hydrogen that comes out of the plane. I would have a hydrogen that goes into the plane. In the E2 mechanism, we are going to remove a hydrogen atom via a proton transfer. The electrons between the carbon-hydrogen bond will now be used to form a pi bond. And the leaving group, which of course will be our halide, will leave. And this is going to leave us with an alkene molecule. The problem that we need to account for is that we know that only certain geometrical arrangements allow the E2 mechanism. Specifically, there are 4 atoms involved in this mechanism. There's the leaving group, there's the hydrogen that is implicated in the proton transfer, and there are the 2 carbons that will eventually form a carbon-carbon double bond. These 4 atoms must be arranged, number 1, in the same plane. And number 2, the leaving group and the hydrogen that's abstracted must be anti relative to one another. So this arrangement is better known as anti-peri, meaning in the same, planar. Now the bond angle, as I've drawn it, appears to be 180 degrees. That would actually be anti-coplanar. We do not need it to be strictly 180 degrees, but it needs to be very close. So typically 175 degrees to 179 degrees is close enough to facilitate a base. And remember, we're going to use a bulky, strong base for this process to remove a hydrogen, which yields its electrons to form the pi bond, which promotes the expulsion of the leaving group. Anti-periplanar geometry is an absolute geometric requirement for an E2 mechanism. The E1 mechanism has no such constraints, but nature simply doesn't utilize E1 mechanisms like it uses E2 mechanisms. In fact, you don't have to look very far in nature to find E2 mechanisms. In the biochemical world, these are called beta eliminations. So a beta elimination is an E2 elimination. One of the best examples is in the reductive biosynthesis of fatty acids. We have to convert carbon-carbon double bonds to carbon-carbon single bonds and vice versa. So there's an example of where a beta elimination occurs in a biological system. Also in Krebs cycle, when we convert fumarase to, or actually when we convert succinate to fumarate, we convert an alcohol to a carbon-carbon double bond. These are all E2 mechanisms. Let's take a closer look at what the major product would be, because what we're going to need to do with this molecule is we're going to need to put it into the Newman projection so that we are confident that the way we're pushing our arrows are actually going to be giving us the type of geometry for the product that we require. This is called stereospecificity. Stereospecificity. And what I want to do now is I want to look at an example where we can have either a cis product or a trans product to show you that we're only going to get one of those two. So I'm just going to change the example to something different. This should be a decent example. So what we want to do is we want to put this into the Newman projection. And so we are going, you can look down any bond that you want, but I'm going to look down this bond right here. So I'm going to call this carbon number 2. And I'm going to call this carbon number 3. And we're simply going to look down this bond and draw the appropriate Newman projection. So when we do this of course is our front carbon. The phenyl group is going to come straight down. The bromine will go up and to the right. The methyl group will go up and to the left. The hydrogen will go up. It's in the same plane. The methyl group down and to the left. The phenyl group down and to the right. The two key atoms that are going to be removed in this molecule are the two atoms I'm circling in purple. They are clearly not anti to one another. So I need to rotate this molecule in such a way where the H and the Br will be anti. To do this, I'm going to hold the back carbon steady and I'll rotate the front carbon 120 degrees. This will in effect move the bromine to this position, the phenyl group to this position, and the methyl group to this position. So rather than redrawing that, I'm just going to erase and redraw the appropriate functional groups. So the bromine is right here. The phenyl group is here. And I'll just label these as methyl groups. Now I can push my arrows. So the base will remove a hydrogen. The electrons will go into this plane. You can't really see that. And the bromine's coming out. And the reason you can't see it is it's like a double bond where one carbon is going into the plane that you can't see and one carbon is an endpoint that you can see. However, what you should be able to easily see is that you've got a phenyl group and its adjacent phenyl group are trans to each other, whereas the two methyl groups are also trans to each other. This is an E double bond. So really the application that you will see in a lot of problems is when we apply this to a cyclohexane ring that's disubstituted. So let's consider these two molecules that are closely related. So we have two diastereomers slash epimers, and what we want to do is to draw the chair conformation and then to analyze what does anti-periplanar mean in the context of cyclohexane. So anti-periplanar equals trans diaxial. What I mean by that is in order for the H and the Br to be anti to one another in the context of cyclohexane in the chair conformation, the leaving group and the hydrogen to be extracted both must be trans to one another. Because they're on adjacent carbons, they also must be in the axial position. Then the E2 mechanism is in play. Extract a proton, make a carbon-carbon double bond, loss of a leaving group to yield the alkene. So let's take a look at both of these molecules. And where I want to begin is to automatically put the bromine in the axial position because I know I'm going to need it there. Now, in the molecule on the left, I have a cis relationship between the methyl group and the bromine. What this means is that the methyl group must go south because the bromine is going south. In other words, if you go back and revisit my equator rule, cis means both are going north or both are going south. No, both of these groups are going south of the equator, or at least they're headed in that direction. Well, this is fine because I have two possible elimination products. I could remove the hydrogen from, I'm going to call this carbon 2, carbon 1, 3, 4, 5, and 6. So with this molecule, there are two possible products. Now, one is going to be more stable than the other, and that's going to be the more substituted alkene. Here's one product. And the second product, this one won't be quite as stable because it's not as substituted. Is this molecule. So the molecule on the left affords two products But of course, the one on the left is my major product via Zaitchep's rule. Now, let's take a look at the molecule on the right. Now I need a trans relationship. Again, the BR has to be axial. But the methyl's trans, so the methyl group forces the hydrogen on carbon 6 to not adopt an anti-periplanar relationship with bromine. So that hydrogen cannot be removed. The only hydrogen that can be removed is the hydrogen from carbon 2, which means we only get one product, and it is the minor product. So if I wanted to produce this molecule exclusively, I would not want to start with the alkyl halide on the right, alkyl halide number 1. I'd want to use molecule number 2 and subject it to E2 elimination. These are classic elimination mechanism questions that one has to address. Okay, so let's wrap up our discussion of elimination by looking at a very important competition. So we have discussed at length the Sn1 versus Sn2 mechanism. We've introduced the E2 mechanism. I have not really introduced the E1. The E1's pretty analogous to an Sn1. You have loss of a leaving group to form a carbocation intermediate. You have a proton transfer that yields an alkene. It's not integrated into nature, therefore we rarely see these kinds of reactions. Normally, if you have a tertiary alcohol and you subject it to a protic acid and heat, that's where you'll see an E1. They're just not very common in nature. So I'm going to look at a series of reactions that could possibly undergo Sn1 or Sn2 or E1 or E2. And then we're going to talk about the mechanisms that will be favored. So one thing about the elimination mechanism that we just discussed, E2 is most reactive where Sn2 is least reactive. So tertiary is most reactive towards E2, then secondary, very little primary, and almost no methyl. So let's look at the special circumstance of having a tertiary substrate. For example, let's look at the product we made at the very beginning of this video. There is no way that it will ever be Sn2. Too bulky. So the question that we have to answer is, what is the nature of the nucleophile slash base? If I have a strong nucleophile slash base, like a hydroxide or an alkoxide or an amide, then this mechanism is going to be E2 all the way. If, however, the nucleophile is weak, there is going to be significant competition between the Sn1 mechanism and the E1 mechanism. Typically, this is going to be in a ratio of about 80% to about 20%. Sn1 and E1 do not discriminate very well. So if I have a strong nucleophile or base, it's E2. The base, as long as it's strong, it really doesn't matter if it's bulky or non-bulky because the substrate's already bulky. If I have a bulky nucleophile and I have a bulky base, then we are going to get a non-Zaitsev product. For example, if I were to subject this molecule to potassium T-butoxide and heat, this base is so bulky that it is going to preferentially remove the most accessible hydrogen. And this product is not called the Zaitsev product, it's called the Hoffman product. So I'll get a more external double bond than if I were to use something like methoxide. Notice I only have 2 alkyl groups that are bonded, whereas if I had a less bulky base, I would have 3 alkyl groups that are bonded. This is called a Zaitsev product. This is called the Hoffman product. So that's our really only dilemma if we have a strong base and a tertiary substrate. If the base is bulky, E2 will predominate and I'll get Hoffman. If the base is not bulky, E2 will predominate and I'll get Zaitsev. All right, now let's look at a secondary substrate. So let's imagine that we have 2-bromobutane. We're really going to have to look at our solvent system. If we're going to discriminate between Sn1 versus Sn2. But before we do that, again, how strong is the base or nucleophile? If I have a strong base, it's going to follow the E2 pathway. If I have a weak base or a weak nucleophile, it's going to follow the Sn1 pathway. Now, when we talk about strong base, if it's not bulky, you're looking at Sn2. But if it's bulky, then you're looking at E2. One of the take-home messages here is that E2 and Sn2 discriminate against each other really, really well. So I can control E2 product or Sn2 product. Sn1 and E1 I have almost no control over, which is, I think, one of the many reasons that nature does not integrate E1 mechanisms into its reactions. So if I have a secondary substrate, first I want to look at the strength of the nucleophile / base. Is it bulky or non-bulky? This will help me determine if it's going to be an E2 or an Sn2. If it favors Sn2, you also want to look at the solvent system. Remember, polar protic will favor Sn1. And the reason it favors Sn1 is that it decreases nucleophile strength. Nucleophile strength has no impact on an Sn1 reaction. Let's write that down. nucleophile strength has no impact on Sn1 kinetics. So a polar protic solvent, and really all this means is that I have hydrogen bonded to a highly electronegative atom. So that means things like water or alcohols or amines. They will solvate both the cation and the anion of the nucleophile, which disfavors Sn2, which in a roundabout sort of way favors Sn1. If, on the other hand, I have a polar aprotic solvent like acetone, and let's take a look at that. Let's say for a moment that we are reacting 2-bromobutane with NaCl. Very weak base, by the way, so E2 is out of the mix. E1 is definitely out of the mix. So is it Sn1 or is it Sn2? It is the acetone solvent that will ultimately make this determination. So I have Na plus and I have Cl minus throughout solution. So I'm just going to draw one Na plus, and acetone will solvate this Na plus via an ion dipole complex. So you'll have a bunch of ion dipoles that stabilize, isolate, and sequester Na plus away from Cl minus. All of these oxygen atoms have a partial negative charge. And so no Na plus interacts with Cl minus. This means this Cl minus is free to act as a nucleophile. We call this a naked nucleophile. This greatly enhances the strength of the nucleophile, which has positively correlated with increasing the rate of an Sn2 reaction. It will have no effect on an Sn1 reaction. So we use the solvent system to discriminate between Sn1 and Sn2 when we have a secondary substrate. What about primary substrates? Primary substrates will almost always be exclusively Sn2. The only way I can make this E2 is if I have a really big, bulky base. So like T-butoxide, or DBU, or pyridine. I can make these E2 mechanisms. So that's the competition we see between substitution and elimination with a variety of different substrates. So this brings to a conclusion the essential information on elimination chemistry. And so now you just need to apply this to whatever questions you're attempting to answer.